When we took a test charge and moved it around in an electric field created by a source charge, we said that we could calculate the change in the electric potential energy of that test charge as it moved around using this equation. So K, Coulomb's constant, product of our two charges. So again, instead of being labeled Q1 and Q2, we've simply relabeled them as the source charge and the test charge. And again, there was this term inside the parentheses, 1 over RF minus 1 over RI, where in this equation, these R's are defined to be distances between charges. So Ri is the initial distance between the charges, RF is the final distance between the charges. We know we can define the change in the electric potential as the change in the electric potential energy over the test charge. So again, we're choosing to cancel out how the test charge impacts how the potential energy is changing. But when I plug all this in, what I see is I end up with a relatively similar equation, but with some important differences. So the change in the electric potential in moving from one point in space to another is given by K. Q is my point charge that's creating the electric field that I'm moving around in. And again, I've still got this 1 over RF minus 1 over RI term in my parentheses. It's just that those R's are now different. So instead of being distances between charges, they're distances from my source charge to both the initial and final points in space. So this gives me the equation to calculate how the potential is changing as I move from one point in space to another in the presence of a point charge. Now we can do the same thing that we did before, which is think about how the electric potential changes as we move near a point charge. And again, that's going to be thinking about basically what's going on with K. Well, it's always positive. Q can be positive or negative, and this term inside parentheses can be positive or negative. So we know that if we move away from the source charge, the final distance from our source charge to the point is greater than the initial distance from our source charge to the point. That means this term in parentheses is negative. So if Q is positive, then moving away from your point charge decreases the electric potential. Positive, positive, negative, that gives me a decrease in the electric potential. If I have a negative source charge, on the other hand, it's still negative inside this parentheses, but now that gets multiplied by a negative Q. Those negatives cancel out. Moving away from a negative source charge increases the electric potential. It's whether my source charge is positive or negative here that I care about. That's that Q. It's a source charge, not a test charge. And if I move away from my positive source charge, the electric potential decreases. If I move away from my negative source charge, the electric potential increases. Well, if I move towards the source charge, then obviously what's going on in that term inside the parentheses, that changes. So my initial distance to the point from my source charge to the point in space is now greater than my final distance to the point in space. The term inside the parentheses is positive, and so now if I have a positive source charge, moving towards that source charge increases the electric potential. If my source charge is negative, moving towards the source charge decreases the electric potential. Again, if we want to talk about the electric potential as we move around in the field created by a point charge, that's the electric potential relative to the 0 point. The 0 point here, again, given the structure of this equation, the 0 point is going to be when we're infinitely far away from the point charge. If we want to calculate the electric potential relative to the point where the electric potential equals 0 infinitely far away from the point charge, we can do it using this equation. So again, the electric potential relative to the 0 point, Coulomb's constant times the charge over the distance from your source charge to the point in space where you're interested in knowing what the electric potential is. Important things about this equation. Again, R is defined to be a positive distance. The potential can be positive if we have a positive source charge, negative if we have a negative source charge, or 0 if we're infinitely far away from the charge. So positive or negative if we're finite distances care about what the charge is. 0 if we're infinitely far away. So just like the potential energy, the potential can be positively valued, negatively valued, or zero. 3. The electric potential depends on one charge, not two. So it only depends on the source charge like the electric field. But unlike the electric field, we don't want that Q in absolute values because we were calculating the magnitude of the electric field with the equation we used there, so we needed Q in absolute values. Here, we don't want Q in absolute values because we want to allow for the fact that if we have a negative source charge, we will have negative potentials. Also, the potential goes like 1 over r, like the potential energy, not like 1 over r squared, like the electric field. So part of what we want to emphasize is that our vector quantities, force and field, go like 1 over r squared. It's our scalar quantities, of which the electric potential is 1, that go like 1 over r. So potential, potential energy, those are scalars, not vectors. They go like 1 over r rather than 1 over r squared, but it also means that when we come to add them, we add them like scalars. And again, this makes life much, much easier because we don't have to worry about directions, coordinate systems, components, any of that. We just say if you're interested in the electric potential at a point in space in the presence of multiple point charges, there's going to be a contribution to the potential from charge 1, there's going to be a contribution to the potential from charge 2, and all I need to do is calculate out those individual potentials and then add them together as numbers. So just like with electric potential energy, the fact that the electric potential is a scalar quantity means dealing with multiple point charges is actually pretty easy. Calculate the individual potential contribution from each charge and just add it together as numbers.